11th of the series. And I am Shashi Srivastava, and I am from VECC Kolkata. So today in this session, we have 5 speakers, 3 talks and 2 short talks. And we have like 25 plus 5 minutes for the talks. And short talks, we have about 12 plus 3. So that would be format. And let me directly go to the first speaker, Professor Satya Majumdar, and I don't think that I need to introduce him to this audience. But anyway, he is a research director at LPTMS Orsay, and his current research interests include extreme value statistics, random matrix theory and its application, record statistics of non-IID processes, among others. Today, Professor Majumdar is going to talk about effective Langevin equation for non-intersecting Brownian bridges. And floor is yours, Professor Majumdar.
Okay. Can you see my slides?
Yes.
Yes.
Okay, so let me thank you, Shashi, and let me start by thanking the organizers for the invitation. And it's a great pleasure to be here, even though it's online. And as I said, this is Calcutta is my hometown, and I'm really missing the good food apart from the the scientific environment of this conference. But anyway, we have to live with it. So today I'm going to talk about effective Langevin equations for non-intersecting Brownian bridges. So there are a lot of technical terms in this title, which I'll explain as I go along. And as we'll see that this problem is also, has quite nice relationship with random matrix theory, which I'll explain. And so this is a sort of recent work which were done in collaboration with Benjamin De Bruyn, who is a graduate student working with myself and my colleague Gregory Scher, and also with our ex-postdoc Jacek Grela, who is now at Krakow, and in collaboration with Henri Orland from Saclay. Okay, so let me start by telling you something that all of you know, a very, very simple question, okay? How do we generate numerically a Brownian motion? Let's say one-dimensional Brownian motion. Everybody knows this answer. So the Brownian motion, so one-dimensional Brownian motion, the position x of t evolves by the Langevin equation, dx dt equal to square root of 2d times eta of t, where eta of t is a Gaussian white noise with 0 mean and delta correlator, and d is the diffusion constant. And it starts from some position x0 equal to a at time t equal to 0. Okay. So you want to generate this trajectory numerically. So what you do, everybody knows, a high school student also knows this. So what you do, you just discretize the time in small time increments delta t, and then the position at time step n is just the position at the previous time step plus a noise, and this noise is just a Gaussian random variable of 0 mean and the variance 2d delta t. Okay, and then you just generate these positions at each time, and then you take the delta t going to small limit, and that's how you generate the trajectory of a Brownian motion. Okay, so it's very simple. But now imagine that you have not a Brownian motion, but a Brownian bridge. What do I mean by bridge? It's the same Brownian motion which starts at the position A at time t equal to 0, but is constrained to reach a final position B at some future time tf. Okay, so that means out of all possible free Brownian motions, you retain only those that arrive at the final position B, but with the correct statistical weight. Okay, and Brownian bridge, of course, is a very important problem because for example, the simplest example is just animals foraging for food. They do typically perform Brownian motion or random walk, and then at the end of the day, they are supposed to come back to their nest. So that's a bridge configuration. Or you can think of a polymer chain grafted between 2 fixed positions in space A and B, of certain length or duration. And so the Brownian bridge is an important problem. And so the question is, how do I generate such a Brownian bridge, which is constrained to reach at the final position B? Okay, of course, naively, you might think that, okay, I'll generate all possible paths and I'll only retain those which arrive at B at time tf. But these are very rare configurations. So this is going to be extremely wasteful. So what you need is some clever algorithm to generate this path in a rejection-free way so that you arrive at the final position B and you generate such trajectories with the correct statistical weight. Okay, so this is a sort of a very general question, and in fact, I mean, this kind of constrained Markov processes, how to generate them. This is a classical problem in probability theory going back to Doob in 1957, and they were studying various Markov chains, and effectively the idea is to write down the effective transition rates, which will automatically ensure that you will reach at your final position B at time TF. Okay. However, often these constrained Markov chains, I mean, they are discrete times and they are not very explicit. So it will be nice to have some explicit, recipe to compute these trajectories. And for Brownian bridge, a simple one-dimensional Brownian bridge, there is a very simple recipe, and the recipe is the following. So what you do, you construct, so x of t is your Brownian motion, free Brownian motion without the bridge constraint, and you construct a new, stochastic process xb of t from x of t by adding a term which is like a drift term t over tf times b minus xtf. So by this construction, you immediately see that at 0, of course, this is 0, and you have xb at 0 is x is a, and when you put t equal to tf, these two terms cancel, and you get xb at time tf is b. So it satisfies the bridge constraints. Moreover, what you can show rigorously that this generates this bridge with the correct statistical weight, meaning that this is a Gaussian process with a prescribed correlator, and this process generates that. Okay, so this is very nice. So you can actually just generate a free Brownian motion by the previous algorithm, discrete time discretization, and then you just add this term, and this will guarantee you that you will generate a Brownian bridge configuration. The problem is that this is not this is very specific to this one-dimensional free Brownian motion. So, for example, if you add a potential term like an Ornstein-Uhlenbeck process, so then this recipe is not going to work. Okay. So what is desirable is to write an explicit Langevin equation in continuous time, which can be easily generalizable to the presence of potentials and so on, and to other processes. And so, how do we write such a effective Langevin equation? In fact, it turns out that for Brownian bridge, you can actually write this effective Langevin equation very simply. And this equation reads the following. So dxb dt again. So again, you have a noise term which is square root of 2d times theta of t. But then you have a drift term, additional drift term, which is b minus xbt by tf minus t. So this drift term actually guarantees that you will actually finally reach b, and with the correct statistical weight. And I'll just in a minute I'll show you the derivation of this result. And this method actually you can easily generalize to Ornstein-Uhlenbeck process and other Markov processes. And so this is some work that we did recently with Henri Orland, and also at the same time by Chetrit and Touchet. So let me just show you how to derive this effective Langevin equation, because it's very simple, and we'll need that later when we talk about multiple walkers. Okay, so what is the derivation? So it's very simple. So the derivation is the following. So you have a Brownian bridge, so it starts at A, and you want to reach B at some future time TF. And so what you do is you split the whole time window is 0 to TF into two parts. Let's say 0 to T and T to TF. So you want the Brownian bridge to reach the position X at time T. So it consists of two parts. It's a Markov part. It doesn't is statistically independent of the left part. So on the left, what you have is a free Brownian motion evolving from A to X at time T. So this is this propagator P of xt starting at A0. And on the right part, you have again a free Brownian motion, independent one, which starts at X at time T, and it reaches the final position B at time TF. And because it's a Markov process, so it's just a product. And the denominator is just a normalization constant, which tells you that the probability distribution of the bridge coordinate X at any time T is normalized to unity if you integrate over X. Okay, so it's very simple. So it's just a product of these two. So why am I doing this? So the idea is to somehow write down a Fokker-Planck equation for this propagator, Brownian bridge propagator, knowing the Fokker-Planck equation for individual Brownian motion. So individual Brownian motion, this propagator you all know. So this is just a simple Gaussian. So position at X at time T, starting at A at time 0, is just a Gaussian like this for free Brownian motion. So then what you do is you know that the P, this solution here, it satisfies just the diffusion equation, forward diffusion equation. Del P del T is D del square P. And this guy, which I call Q, and I think of time going backwards, then Q actually satisfies the same diffusion equation, but with a negative thing here, because T is simply TF minus T. That's why there is a negative sign. Okay. So now you look at the product, which is this P tilde, which is P times Q. Okay, normalization constant is just a constant, you don't care. And so you just take the del P del T and you just use equations for P and Q. And then very simply, just a little exercise will show you that this del P tilde del T, which is the Brownian bridge, it satisfies again the same diffusive term here, but there is an additional drift term which depends on this free Brownian propagator Q. Okay, but since you know the free Brownian propagator Q, so therefore, and from this, the Fokker-Planck equation, you can immediately read off the effective Langevin equation, because this is a diffusion term, so there should be a noise, a Gaussian white noise, and this is a drift term, and so the drift term therefore reads 2D del x del log Q. And knowing Q explicitly, you can then just calculate this drift term, and this automatically guarantees you that you will reach B and with the correct statistical weight. Okay, so that's what this equation is about here that I showed you. And as you can see, immediately you can generalize to other processes. All you need to know is for the free part, you just need the propagator and the associated Fokker-Planck equation, and then you can write the effective Langevin equation for the bridge process. Okay, so this is the general idea. So with this background, so now the question I want to ask in this talk today is that, is it possible to generalize this effective Langevin equation approach from a single Brownian bridge to multiple Brownian bridges with some interaction between them? Okay. Now, the reason we are interested in this problem is actually the setting for this multiple Brownian bridge problem is actually what is called a very famous problem in statistical physics. So this is called the non-intersecting Brownian motions or Brownian bridges, and it has a long history. It sort of goes back first to probability theory by Carlin and MacGregor, and in physics literature it was first introduced by Dejean in 1968, and then later it was popularized by Michael Fisher in the name of Vicious Walker. So basically these are, you have n independent Brownian motions, but with the constraint that they cannot cross each other. So that's what is called the vicious Brownian motion. And Michael Fisher called it a vicious walker because, if two walkers meet, they just kill each other. So therefore, if they all want to survive, then you have to ensure that they don't cross each other. Okay? And since then, this problem has appeared in many, many different, contexts. In particular, Michael Fisher studied this as to study the incommensurate commensurate phase transitions in solids. And then it also appears in growth problems, in KPZ growth problems, Kardar-Parisi-Zhang problems. It appears in 2D Young-Mills gauge theory, and it appears in many, many different problems. So I'll just show you some examples. So let me go back first to the work by Dejean in 1968. So Dejean was interested in studying the lipid, multi-layer problems, which are separated by interfaces. So he came up with a very simple toy model. So the toy model is the following. So you have this, it's fibers, so-called, he called them fibers. So these fibers are like, polymer chains, if you like. And so they are supposed to mimic the interfaces between different layers of liquids. And they are stretched between two glass plates. So these are the two glass plates, parallel plates, and more or less grafted at equidistant points on both sides. And in between, they can fluctuate, these lines, due to thermal fluctuations, but the constraint is that they cannot cross each other. Okay? So the different chains cannot intersect each other. Okay? So if you think of this direction x as a time direction, then these are just the trajectories of Brownian motion that cannot intersect each other. Okay, and they are in a bridge constraint. They're going from one initial configuration to, and this is a flat geometry because they're equidistant points to final equidistant points. And Dejean was interested in the following question. He was interested that at any intermediate time t, or x if you like, if I look at the positions of these particles, what can I say about these positions? In particular, for example, simplest question is the density. What's the average density of this system of particles at any intermediate time t? Okay, he could not calculate this density because he understood that there's a connection to fermionic path integrals of this problem, but the density he could not compute because at that time the connection to random matrix theory was unknown. And what I'll show you is that using random matrix theory, you can actually compute this density explicitly. Okay, so this was the Dijon problem. And then, this has also, these non-intersecting Brownian bridges also appear in experimental systems. So this is the picture from the Maryland group of Ellen Williams. So basically, if you take a crystal and if you cut the crystal at an angle, you get what is called the vicinal surface. And so what you see on the left side is the pictures of terraces of atoms, which are separated by, these lines here, the terrace step edges. And these step edges, you can think of them again, the trajectories of non-intersecting Brownian bridges going from one side to another side. And on the right, what you see is a STM, these scanning tunneling microscopic pictures from the top view. And you can see these, these fluctuating lines, which do not intersect each other. And you can actually measure their fluctuations and so on. Okay. And also this problem appears in computer science. So let me just, in fact, in computer science, one of the, central problem was to come up with an algorithm to generate such paths, non-intersecting paths. And these people, Bonich and Mosba, so they studied the lattice paths, so non-intersecting lattice paths going from one end to another end. And they looked at a particular geometry, which is that, all the walkers more or less start at the same point. So these are not equidistant points. So they are exactly identical. They start from the same lattice site. And each of them is doing random walk, except to the constraint that two random walkers cannot be on the same site. And they come back to the same initial position origin at some final time TF. So they came up with an algorithm, but it was a bit complicated because, they computed the effective transition rates from one step to another step for all these paths together. And it was not so easy to implement this algorithm so much. Okay, and this particular geometry, there's a name for it. It's called the watermelon geometry. Watermelon because these walker trajectories, they look like the stripes of a watermelon. Okay, and I'll come back to this watermelon in a minute. So there are many different contexts in which this problem appears, and so the two questions that I want to address in this talk. So first is an algorithmic question. I want to generate these non-intersecting Brownian paths going from equidistant points, A1, A2, A3, AN, let's say, to B1, B2, B3, Bn at some fixed future time TF, but with the constraint that they cannot intersect each other. So there are two constraints here. One is a geometry constraint, which is the bridge constraint, that they have to finally reach some fixed configuration. And then there's a dynamical constraint that they cannot cross each other at an intermediate time. So how do we generate numerically such paths in an efficient, sort of rejection-free algorithm? I mean, as I said, you can generate such paths and throw away most of the paths because these are rare configurations. So that would be stupid and, really costly algorithm. So can we, for example, write down an effective Lanzmann equation the way we did it for a single particle for this assembly of non-intersecting Brownian bridges? So that's the first question. And the second question is the Dijon's question, that is, if I'm at a fixed time t and I look at the positions of these particles, x1, x2, x3, xn, what can I say in general about the joint distribution of these positions? And in particular, can I calculate the density? That's the first one-point function. Can I calculate the average density of these particles at an intermediate time t? Okay? So these are the two questions that I want to address in this talk. And as I said, a special case corresponds to when the initial positions are all collapse to the origin and some final positions also collapse to the origin. And this is called the watermelon geometry. So for the watermelon geometry, many things are known. So let me just first tell you this, what is known about watermelon geometry. So watermelon geometry means they start at the origin, they arrive at the origin, and in between, they stay non-intersecting. Okay? So in this case, and this is the connection to random matrix theory, in this case, you can actually compute exactly the joint distribution of the positions of the points at an intermediate fixed time t. And I'm not going to show you the derivation, but just to tell you the result. So the result is that the joint distribution has a Gaussian part with a variance, which is just t times tf minus t divided by tf. And then there's a van der Monde term, xi minus xj squared. This is because effectively they repel each other, they cannot cross each other. And there's a xi minus xj squared. So this is the exact joint distribution at any intermediate time t. And those of you who are familiar with random matrix theory immediately will recognize that this is nothing, if you think of xi by sigma t, the scaled positions, as the eigenvalues of a n by n Gaussian Hermitian random matrix, so-called the GUE ensemble. And there it's known that the joint distribution of eigenvalues has exactly the same form. And there we know that the density, for example, at a fixed time t, if I look at the eigenvalue density, so average density is given by the Wigner's semicircular law. So that means, all these points, there's more points near the center and less near the edges. And this is just the Wigner's semicircular law. Okay. So this is Wigner's semicircular at all intermediate time t. So this is the watermelon geometry for which many results are known. And in particular, if you look at the top guy, it is distributed as Tracy-Williams distribution and so on and so forth. So the question is, what happens when we don't have this, this watermelon geometry, but they are uniformly distributed at time t equal to 0 and at time t equal to tf, which is the original Huygens problem. Okay, so this is our problem. And so what I'll do is, I don't have time to explain to you all the details of the results. It's a short talk, so I'll just just give you an outline of how we proceed. So there, as you remember, there are two questions: how to generate such paths, algorithmic question, and the second question is, can we calculate the density when these AIs and BIs are uniformly distributed? Okay, so I hope the problem is clear. And now I just want to tell you, just outline our method of derivation and the results without telling you any details. So so this is the problem. So I have these vicious Brownian bridges going from more or less equidistant flat geometry to flat geometry. And I want to first generate an algorithm which will efficiently generate these paths in a rejection-free way. Can I do it? So the answer is, if I try to do it for the vicious Brownian bridge, again, you have two problems here. One is the bridge constraint, and other is the non-intersection constraint. And this non-intersection constraint is very difficult to implement in an effective Langevin equation. So what we do first is that we map this vicious Brownian bridge to an exact mapping to something called Dyson-Brownian motion bridge with a parameter which is called beta equal to 2. This is an exact mapping. So what is the advantage of this mapping? The advantage of this mapping is that in this second set of problems, where again you have some kind of interacting particle system, but here this non-intersection is explicit. I don't have to implement it separately. And so all I have to do is, for the Dyson-Brownian bridge, I have to ensure that it reaches the bridge configuration. Okay, and that I can use the effective Langevin equation. So the point is that first this mapping, and then for this later system, you can actually write down an explicit Langevin equation, more or less following the method that I used for single Brownian motion, and to generate the efficient algorithm for this flat-to-flat geometry. Okay, so we can generate this in a totally rejection-free in 1 minute, these paths. And moreover, the second thing is that this explicit Langevin equation, we can also use it, and again, this is technical part, I'm not going to the details, to calculate the density exactly at any intermediate time t. Okay, so this is the sort of main result. And so let me first tell you what is the difference between the vicious Brownian bridge and Dyson-Brownian bridge in just 2 minutes. And it's very simple, actually. So on the left, you have vicious Brownian bridge. That means, the just ordinary random walker. So each of the walker is evolving independently as a Brownian motion. And here I choose the diffusion constant to be 1 over root n for simplicity. And this is just a Gaussian white noise. And with the constraint that they cannot cross each other, and that they have to reach some final positions BIs. Okay. Now this constraint of non-intersection, which means that they have to be always ordered. If I start in the ordered position, they have to be always ordered x1 less than x2 less than xn at all time t, intermediate time t. Okay. So what you have to do to solve this problem, to calculate the propagator, you have to first write down the Fokker-Planck equation for this system, and this non-intersection constraint enters through a Dirichlet boundary condition at the edges of your while chamber. That means, in this ordered sector, whenever any two coordinates become equal, you have to set P probability to be 0. So this is why this problem is related to fermions, actually. Okay, and so this is the non-intersection. So non-intersection constraint comes to the boundary by implementing to the Dirichlet boundary. It's not explicit in the equation of motion. Okay. On the other hand, Dyson-Brownian motion is a separate system of interacting particles, which evolved by the following Langevin equation. So d lambda I dt is there's this term, which is 1 over lambda I t minus lambda jt, plus a noise term, and this parameter beta appears in the amplitude of this noise, and these are again Gaussian white noises. Now this term here, Dyson was interested because he was interested in putting, how to see the dynamics of the eigenvalues of a random matrix theory. But effectively, you can just think of this as a particle systems with coordinates evolved by this motion. And this term here, the first term, the drift term here, it actually automatically ensures that they do not cross each other. Okay, because when they were trying to cross each other, there's infinite repulsion between these that comes from the drift term. And so this automatically ensures that they cannot cross each other. Okay, so the difference between these two is that here the non-intersection constraint comes explicitly in the equation of motion, whereas here it comes to the boundary term. Okay, and but what we show is that you can actually make an exact mapping between these two problems, and you can show that the propagator, that means the probability distribution of the joint distribution of the lambda is in this problem, that is exactly equal to the joint distribution of the Dyson-Brownian bridge when you choose this parameter beta equal to 2. And thanks to this mapping, so now we can actually use this guy here and write an explicit Langevin equation to take into account the bridge constraint. And again, I will not show you the details, but this is the explicit Langevin equation, which was derived in this paper. So there are two terms in this equation of motion. So the first term is a drift term, which tells you that it will reach the bridge configuration. Okay, these are uniformly distributed, the initial and final positions, and this is the term which actually ensures that they do not intersect each other at any intermediate time t. Okay, so this is the main result. Yes,
but we have only 2 minutes left in the talk.
Yes, I'm just finishing. So this is the sort of main result. And moreover, I mean, using this result, I mean, okay, I will not show you the details, but you can actually write down the resolvent of the Green's function of this equation, and from the Green's function, you can actually compute the density. Okay? So this is the sort of main result. And so let me just tell you the results. So what you can show is that by this algorithm, you can generate these paths, non-intersecting paths, bridge paths, going from flat to flat geometry. And you can actually calculate the support of this density, lambda minus t and lambda plus t. They are supported over a finite support. And this is explicit. You can actually compute the equations for this lambda plus t and lambda minus t explicitly. And they are given a little bit complicated, but explicit. And also, you can compute this density at any intermediate time t. In particular, for example, at the mid time, it's a symmetric around tf by 2. So at the center exactly, you can, this center, it turns out that this is also related to other problems in matrix models, this so-called Chern-Simons model. And you can compute the density. It looks like semicircle, but it's not a semicircle. So we can recover this known result at this center. But we can also calculate the density at any other time. For example, TF by 3, TF by 4, all rational points, we can get explicit results for this density. They all look like a little bit like semicircle, but they're not. I mean, the actual formula is much more detailed. And so this gives us access to all the density at any intermediate time, and this was the problem which was open for a very long time. So let me just summarize the conclusions. Basically, by using an exact mapping between the viscous Brownian bridges and Dyson-Brownian motion with beta equal to 2, we are able to write, first of all, an effective Langevin equation to generate this viscous Brownian bridge path. Because if I generate Dyson-Brownian bridge, that automatically guarantees through our mapping a viscous Brownian bridge configuration. So we can generate them very efficiently. And moreover, and this has been recently, extended to other discrete time random bridges. And moreover, as I said, using the explicit Langevin equation, we can write an equation for Green's function. We can solve it by Burger's equation. I mean, okay, these are details. And from that, we can actually extract the density at any intermediate time, finite time t. And at special points, and these are at each time t, the joint distribution, it gives rise to new matrix models. And in some particular limits, like TF by 2, it's related to some other known models of matrix models, like Chern-Simons model or something called Stieltjes-Wiegert polynomial models, or Borodin-Mutalev ensemble in nanometric theory, and also to Harish-Chandra-Dixon-Zuber integrals. These are just technical terms. I mean, I don't have time to tell you all the details of this, but the main point is that, at special values of our new random matrix ensemble, you can actually recover some known matrix models that have been already discussed in the literature. But it gives a full perspective and solution for this interesting problem that was basically started by Dejan. Okay, I think with that, I don't have any more time to talk about. So thank you very much for your attention.
Thanks, Professor Majumdar, for a wonderful talk. We have time for 1 or 2 quick questions. Okay. I can see one raised hand. And Tonello, yeah, please.
Yes. Hi, Satya. So just a quick question. If you say that the distribution of the positions it follows the GUE distribution, why isn't it semicircle?
No. Distribution follows. You see these things is distribution follows GUE only in the case of watermelon geometry. Only when the initial positions and final positions are all.
Okay, so that's the condition. So in the case where the initial condition,
when they are differently distributed, nobody knows what the joint distribution is except for this flat geometry, for which you can actually calculate the joint distribution explicitly.
Okay, so but in this case, it is a semicircle.
It is a semicircle, yes. In this case, it is a semicircle. Absolutely. That's what I said, witness semicircle.
Thanks.
Yeah.
Okay. Maybe one last question. Department of Physical Sciences seminar.
PK. Yeah, PK. So on the surface growth one, their layers grow at different levels. So they're not restricting each other. It's only that in the picture they look like.
Yes. No, the layers go, but if you look at the interface, the interface between the layers, okay. So like polynuclear growth model, if you look at the different layers, and if you look at the lines that separate different layers, these lines you can interpret them. I mean, not only interpret, you can actually show them that they are exactly non-intersecting Brownian motions.
Okay. But they're not in the same space. They're not in the same space as you see here,
They're not the same phase.
Same space. They're not restricting each other. They can actually grow wherever they like.
No, they can grow, but I mean, you have to take from a side view basically. So, if you see the height of the layers, different layers, so they are like the positions of these particles. Okay.
Okay. Maybe one last question by I think Abhishek was raising the hand.
Okay, so Shota, in this, why did you need? So where did this beta equal to 2 condition come? I mean.
Yeah, so beta equal to 2 condition comes from the fact that so you see this Dyson-Brownian motion. When you write down how do you show the mapping between the two? Basically, when you write down this satisfies on the left hand side, it satisfies the Fokker-Planck equation with the Dirichlet boundary conditions. Okay, just the diffusion equation. Now on the right part, when you write down the Fokker-Planck equation for lambda i's, so what you see is that there is an extra term apart from the diffusion, and this extra term, the coefficient, is actually beta minus 2. So only when you beta equal to 2, the extra term goes away. Otherwise, this extra term is there, and this extra term actually gives rise to a Fokker-Planck equation, which is 1 over xi lambda I minus lambda j square. So it's more like the Calagione model in general. Okay. So only for beta equal to 2, that term goes away, and then you can show that they are exactly related to each other.
Okay. Yeah. Thanks.
I'm sorry, we can't take any more questions. Let us thank Professor Majumdar once again for a wonderful talk. And let me move on to our second speaker of the session, Professor Thomas Guhr. Professor Thomas Guhr, needs no introduction in the community of random matrix theory. But let me just say a few words. Professor Guhr leads the Statistical Physics of Complex System group of University of Duisburg-Essen. And his current research interests include quantum chaos and random matrix models, many body system and quantum chaos, approach to QCD from RMT. These are just one of the few. And today he is going to talk about statistical topology, winding numbers of a parametric chiral unitary random matrix ensemble. Professor Guhr, please.
Yeah, thank you very much for the invitation. It's a great pleasure to be here and to have the opportunity to give this talk. Outline. Winding numbers, I think it's well known, topological invariance, and it's also known that chirality is a fundamental symmetry in physics. These are well-developed concepts, and I will, just to illustrate that, give 2 examples. So the question we want to ask now is, what is their role in a statistical setting? Or put differently, we want to look for generic universal features if we combine these concepts. And our tool will be random matrices, because we know that random matrices give universal answers. So we will see what comes out. So I'm not going to show you a comparison of, at the end of my talk, of some calculations and some empirical data or so. So the whole project is inspired by the fact that all these concepts are fundamental, and we just wanted to combine them. So the merger of these three concepts, that is the purpose of my talk. These are my collaborators, the late Piotr Braun, Nico Hahn, Daniel Waldner, and myself from the University of Duisburg-Essen, and Omri Gatt from the Hebrew University in Jerusalem. And here you see our first publication on this. Merger of three concepts. So let's begin with the winding number. I think we all know from complex analysis that the winding number W of a point that I in the complex plane counts how many times this point is encircled on some path gamma. So we distinguish between counterclockwise and clockwise encirclements. So we get positive and negative contributions. So that is a signed winding number we are talking about. Simple example. Here you see 3 points, Z1, Z2, Z3, and a curve gamma. And you see the winding number of Z1 is just 0 because it's not encircled at all. Z2 is encircled once. Winding number is 1. Z3 is encircled twice. So the winding number is 2. So the winding number is always integer, and we can calculate it by this integral in the complex plane. The point is now, it is a topological constant or invariant or a quantum number, because you can now deform this curve gamma just as you like, provided that you do not cross over one of those singularities here. But all these deformed curves will give the same winding numbers. Now, an example for chirality in condensed matter physics. Here I will briefly speak about the famous Kitaev chain. So it's a chain of spinless electrons with next neighbor hopping and superconductive pairing. Here you see the Hamiltonian, so that is a hopping term, T is a hopping strength. That term goes with the diagonal term, goes with the chemical potential mu, and these are the pairing terms, so with delta being the pairing potential. Now, if I picture this chain now in the following way, so the grayish blobs here are the electrons, then I can use the fact that each fermion can be written as a linear combination of two Majoranas. But then, if you write it down as a Hamiltonian, you see you have options. You can do the pairing in such a way here as in the first chain, and you can do it in this way, the second chain. And you see there's a difference. Here I have only paired Majoranas, and here I have at the end two unpaired Majorana fermions. And it turns out that these two configurations of doing it are really robust. So we can view them as phases. I'll show you how that works. So let us go to a Fourier space representation. So we evaluate the Bloch, Bogoliubov-de Gennes Hamiltonian, and we observe that it can be written in this. I mean, I'm cite literature here. That is not our work, of course. I mean, this is textbook stuff. So that is the Hamiltonian now. K is a wave number, and I can write it as a scalar product with a vector D in 3 dimensions here. And sigma is a vector of the Pauli matrices. And it turns out that the first component of D is 0. So I have only 2 non-zero components here involving the pairing potential, the hopping strengths, the chemical potential, and of course also the wave number. Now, if you look a bit deeper into it, you see that this precise form, including the fact that we have a 0 here, is simply due to the fact that this Hamiltonian has chiral symmetry. So it anti-commutes with a chiral operator, which in this simple form is just a 2x2 matrix with 1 and -1 on the diagonal. And now let's see what kind of implications that has. So we want to plot this vector here in the YZ plane, and together with that we want to plot the dispersion relation, so energy as a function of the wave number. So that you see here. So it's a little animation, so it works. What you now see here, that is this vector D in the dy and dz plane. And what you see here is a change of the ratio of the hopping strength and the pairing potential. And here you see the dispersion relation. And if you look carefully, you see there are actually 2 regimes. One regime is that this ellipse does not include the origin, and the other one is that the ellipse includes the origin. And according to what I said about the winding number, the first case, is a case where winding number is 0, and the second one is where winding number is 1, and these actually correspond directly to these two topological phases, which I showed in this illustration with these two versions of pairing or not pairing the Majoranas. And you also see the point when the ellipse touches here the y-axis, that is a phase transition point. Okay. Another example for chiral symmetry, that is quantum chromodynamics, the theory of the strong interaction. So we have quarks and gluons, and we know that for massless quarks, the Dirac operator d slash, so the slash comes because we sum over the gamma matrices, not really important here, has a chiral symmetry, which means it again anti-commutes with the chiral operator c, which in that form is just this combination of the unit operator and minus the unit operator. For massive quarks, however, so for the reality, chiral symmetry is explicitly broken. However, let me remind you that the largest part of the constituent quark masses, so about 300 MeVs per c squared, comes from spontaneous chiral symmetry breaking. So as in this beautiful Nambu-Yonah-Lassigno model. Does it make sense now to think of that in a statistical setting? Yes, that has been put forward about 30 years ago by Jack Weberscott and Ed Shuryak. So let's look at chiral random matrix theory now. So instead of the operator, we look at the Dirac matrix. And again, it must anti-commute with the chiral operator, which in that case is just this matrix. 1n is the n by n unit matrix. So the Dirac matrix is a 2n by 2n matrix. Now, if it anti-commutes, it means I can write it in this form, in the eigenbasis of the chiral operator. And in the random matrix model, we assume that K has no symmetry, so it's just an n by n random matrix. And now we have choices. We can make the entries complex, and then we have the chiral GUE. We can make them real. We have the chiral GOE, or we can make them quaternion, and then we have the chiral GSE. Does it make sense? Yeah. Here I show you an historical picture on one of the very first papers by Jacobus Weberscott. You see here the lattice gauge calculation. So you really calculate QCD on the lattice. So these are very demanding calculations. And we look into the eigenvalue density near 0. Yeah? I mean, these chiral models all have a hard edge. So, I mean, there's the smallest eigenvalue. And what you see here is a histogram are the data of this lattice gauge calculation. And the dots here, this is chiral random matrix theory. So what you see here is the fluctuations of the first, the second, and the third eigenvalue. So it works very, very well. So we get the spectral statistics very well. And even nowadays, it's so that people determine the chiral condensate, so the order parameter, from fitting the chiral random matrix result to the empirical data or to the data of the lattice gauge calculation. Okay, I promised that we want to combine these three concepts. So what is the idea? Well, winding number chirality random matrices, so it is an assemblage that yields statistical topology. What do we expect? Well, as I already said, random matrices have the beautiful feature of being universal if you look at them in the right way. So what we expect here are universal statistical observables. So I want to pose the random matrix problem in the following way. So there is some background noise. Oh, now it's getting better. So we write down a matrix field. Here I call it Hamiltonian, but I could call it Diracian, so it's not important. In this way, so we let H and the case depend on some parameter P in such a way that it's always chiral. And the P lives on a circle, so a one-dimensional manifold S1. So the winding number, as I already said, is a topologically invariant, and we can write it in this setting here as this integral over the winding number density. So winding number density is a derivative of the logarithm of det of k. So it is 1 over det of k times the derivative of det of k. So if you insert that, you see that it's nothing else but Cauchy's argument principle, well known from complex analysis. Yeah? And then we know from complex analysis that W must be an integer, positive or negative. Okay, now, so far I said we have some parameter P, but I have not really specified what kind of realization of this parametric ensemble we want to have. And let's do something very simple. So K1 and K2 are n by n complex matrices chosen independently from Gaussian chiral ensembles. I could also say from Geneva ensembles, that is equivalent in that case. And the parameter depends, we just model by a cosine and a sine here. So the chiral Hamiltonian has this form. It is a linear combination or parametric combination of two independent chiral Gaussian unitary ensembles. Good, so that is what we now want to calculate, the observables we want to study. We want to look at this from the point of view of a random matrix model. So we want to ensemble average over the K1 and the K2. I still owe you a precise definition of that, comes in a minute. And we want to work out, first of all, the K-point parametric correlators of the winding number density. So this object here, ensemble averaged. And let me point out here that this is really different from the well-known Altschuler type of parametric correlators. So they looked about 30 years ago on parametric correlators of the level motion. It's just a completely different quantity. We look here at the winding number or the winding number densities. I will show you that one can very directly calculate the distribution of the winding numbers. And of course, the issue will be, how about universality for large matrix dimension n? Okay, let's first go for the mathematically most difficult project, but actually it's not so difficult. It's the K-point parametric correlators of the winding number density. So we manipulate the expression here. So ln det k of p. The derivative of that will give the winding number density. Now, I have this linear combination of K1 and K2, so I just pull out K1 and sine of p, and then I get, because of the logarithm, these three terms. And you see the last term involves ln det, the cotangent of p, and the really, really odd-looking matrix K1 to the minus 1 times K2. Put differently, I can write it in this form if I say that Zn are the complex eigenvalues of this strange matrix. So the winding number density is now the derivative, and a very nice feature is this term drops out. This term gives a simple contribution this here, and only the last term contains something involving these eigenvalues. The good news is now that the eigenvalues of this matrix are actually well known in the literature, and also the joint PDF and the random matrix theory involved with it. That is known to Forrester and Krishnendu, because this can be viewed as some kind of a spherical ensemble. So here you see the joint PDF involving the Vandermonde determinant, which we already have seen in the previous talk, now of complex arguments. So see, all sets are complex variables here. And this term here, I mean, it looks a bit like a stereographic projection. So that is where this name spherical ensemble comes from. So these are all Euler beta functions here, and here's Vandermonde. So please let me point out that you see from this expression here that this joint PDF does not only depend on the moduli, it also depends crucially on the faces. Volume element, just the product of all these volume elements on these complex planes, and this is then the precise definition of the ensemble average. Okay, I don't want to go through the whole calculation because it's not very difficult, but it's just messy. But just to give you a flavor of it, let's introduce shifted winding number density by removing this little bit annoying term here. So the y, so the shifted winding number density is just this sum here. And then we can rewrite the correlators as a sum over the permutation group, and with these averages over all these shifted winding number densities. If I insert this now here, you see I have a very unpleasant combination of all these fractions here. But one can pull them apart by using standard methods. And at the end of the day, you will see that only the ensemble average of such a term matters, and we can then put together, assemble the whole correlator just by these functions. Conveniently, it is given as a k by k determinant involving a kernel L, and this kernel involves once more the Euler beta function, and here functions which we call incomplete Euler beta functions. So it's just this integral here, and if I put QL to infinity, you see I get 1 due to the normalization, so this is why we call it incomplete Euler beta functions. Okay, so that is the result, but now let's look at some examples. So the 1-point function is 0, that should not surprise you, and we are not talking about spectral statistics here. So the 1-point function does not yield after integration the level number or anything like that. I mean, and if you look at the parametric realization that we chose, it's kind of natural due to symmetries that this must be 0. The 2-point function is a bit more involved. And here we notice that it only depends on the differences. But that is also natural. If you look at the whole project, and it's a bit more complicated, I just want to mention it because it's fairly obvious. We are always on the ring. So all these parameters P1 to Pk live on a ring. So we have some kind of rotation or translation invariance on the ring. So everything can only depend on the differences. Okay, but our question was, are there universalities? And this we want to answer now. Turns out that it's a bit messy due to these sums over the permutation group for the general k-point correlation function, but for the 2-point function, we already find something nice. And this is what I want to show you. What do we know? For spectral correlations, we know that they are universal in random matrix theory on the scale of the local mean level spacing, which is, if we choose a standard normalization, proportional to 1 over square root of n. We also know that the parametric correlations, Altshuler style, are universal on the scale of the local level velocity. In our type of model, we can show rather quickly that this cannot really be important here because the average of that gives 1. So let's try a rescaling involving n. So we choose a new variable psi I as pi times n to the alpha, where alpha is just a positive number. And now we ask the question, if I now replace a pi with the psi's in the 2-point correlation function, and of course I have to take care of the differentials also because it's John PDF. And if I calculate the limit n to infinity, do I get something reasonable on the right-hand side? So put differently, do I get some function f2 which is non-trivial? And the answer is yes. Actually, I do not just get one function, I get regimes. So for alpha larger than 0 but smaller than 1/2, I get this function here for all alphas. For alpha equal to 1/2, I get this function. And for alpha larger than 1/2, I get 0. So I get regimes of universality here. So let's look at alpha equals 1 over 6. And red curve is the limit, which I showed. And the blue curves are for different n. And here's alpha 1/2. So that is this Gaussian, 1 minus Gaussian divided by the difference squared function. And here blue are again different n results. So that is what we get. So we get regimes. We do not have a full interpretation for what that really means, but I just show you the result. So now we calculate the winding number distribution. So that is actually a fairly easy task. So it turns out that it's helpful to introduce s equals I to the ip on the circle as a complex variable. And if I write the determinant of our random matrix model as a function of s, I get this here. And here you see immediately, it has in S a pole of order n, and it has zeros which come in pairs, and n of them. So the set n can be identified with the eigenvalues of the spherical ensemble. So there is a small modification which disappears if you look at the ensemble average. So therefore I say I can identify these eigenvalues here with the eigenvalues of the spherical ensemble. And now here we use again Cauchy's argument principle. So I write down the winding number as this integral over the complex plane for s integrating on the curve with modulus s equals 1. And I know what the result is. That is the Cauchy argument principle. We know that it's a difference of zeros and poles inside the unit circle. We have a pole of order n at 0, and we have the zeros coming in pairs. Let's say we have m of them inside the unit circle, so that is our winding number. M equals 2m minus n. All what we have to do is to calculate the probability that m eigenvalues are inside the unit circle and rest outside, which is nothing but integrating m of these eigenvalues inside the circle and the remaining ones outside the circle. And here is a joint PDF. And the result is very simple. It's a 2-line calculation. And it again involves the incomplete beta functions which we introduced. So now taking care of some permutations, so that is a binomial coefficient, we have now our winding number distribution. And the question is again, are there universalities? The mean value is 0, of course, because of the symmetries. The variance is this ratio of double factorials, and for large n, it is going like square root of n. That is interesting, because if we now look at the distribution as a function of w divided by n to the 1/4th power, not square root of n to the 1/4. For large n, we see that we get a Gaussian. So far, we have only numerical evidence. My collaborator Omnigat has some analytical reasoning, and we are just working on putting that together to make a more serious argument out of it. But numerically, this Gaussian is very well confirmed. Yeah. So I come to my conclusions. So what have we seen? We try to merge three concepts: winding number, chirality, and random matrices. I introduced the parametric model combining two independent chiral Gaussian unitary ensembles as a specific realization of, in principle, infinitely big class of such models, which we could use for looking at such parametric statistics. I showed you some exact results for the winding number density correlators and also for the winding number distribution. I showed you that we do not have just universality for the two-point correlator. We have regimes of universality. Admittedly, right now we do not have a full interpretation of all that. I mean, all has to do with, with the concepts that I mentioned here, but we have not really sorted it out, how we can interpret all these universalities or these different regimes of universalities here. And we have found a large n universality for the winding number distribution. So we hope that these universal results that we found will also have application for experimental data or so. Right now, it is something like explorative statistical physics or mathematical physics. Thank you very much for your attention.
Thank you, Professor Guhr, for a nice and wonderful talk. And we have, I think, more than about 5 minutes or so we can take up questions. Do you have any questions in YouTube live link? I mean,
not there. I mean, it will be posted here.
okay. Okay. If not, let me kind of, ask a sort of naive question about this winding number statistics. So how should I, you started with chiral ensembles, and each eigenvalues are like doubly degenerate. That's like starting point. And now, how should I interpret this winding numbers of each eigenvalues and how to, how to make sense of this? That what this distribution is basically telling me.
So so that is a winding number, yeah, and that is for a fixed curve gamma, yeah.
Right.
In the model that I introduced, first of all, we generalized it to a higher dimensional problem. Yeah? And then, of course, in the ensemble average, the different matrices. So here I have my random matrix model. Here. So the different matrices change in the ensemble average, which means I get an ensemble of such curves in some sense. Huh? Okay. So I want to ask the question, what is then the distribution coming out for the winding number or for the correlator for the winding number density if I look at modifications of these curves in the more complicated matrix setting here. And as I said, I mean, it is very much inspired. So I now give a motivation that we, of course, have in mind. It is very much inspired by this. So if I look at this Hamiltonian here, you see that sine k and cosine k play bit the role of the sine p and cosine p which are introduced. So put differently, if I make such a Hamiltonian random now, so by introducing this order, I come already quite close to the model which I set up formally with random matrices. So this is, of course, an active research line. So that is what we want to look at next.
Okay. Thanks. May I ask like a related question to it? Like, since you have different, so in your random matrix model, you have parameters, right? And this, you have shown the universality on scale of like root n. I mean, you have n to the power, different powers you have, right?
Yeah, let me find the transparency. Here it is. Yeah.
Yeah. So I mean, this universality is for like everything, or you just have for the 2-point correlation function?
Yeah, good question. Thank you. Right now, we only have it for the 2-point function because that is such a simple function. So it's just a simple algebra. And we are struggling a bit with showing this universality for the k-point function, because the k-point function is the linear combination of such horrendously complicated terms. It's not difficult, it's just messy. And here again, we have now, if we plug that in here, so we have like a double sum over the permutation group. You know, I'm very convinced that we must have universality for all k, so also for the k-point correlation function. But right now, we are struggling with the mathematics to actually show it.
Okay.
So these are very recent results, all these things. It's our first paper on the matter, and we are still working on it very much.
Okay, thanks. So if, I mean, I can't see any other question in the Meet link. So let me thank Professor Guhr once again for a wonderful talk, and move on to our next speaker, Professor Arul Lakshminarayan. Yeah, I can see him. Professor Arul Lakshminarayan is a professor in Department of Physics, IIT Madras, and his current research interest is basically Hamiltonian chaos, quantum chaos, entanglement, quantum information theory, and random matrix theory, which he uses quite a lot nowadays in predicting a lot of entanglement-related results. So let's hear him on random and dual unitary quantum circuits. Professor Lakshminarayan, please.
Thank you very much, Shashi. Can you hear me and see my slides?
Yeah,
Yes, we can, yes.
perfectly well.
Yes.
Thanks. Thank you very much for the introduction, for the invitation. Thanks to all the organizers for putting together what promises to be a very interesting conference. I'm going to talk about some work done with my PhD student, Sohail Ahmad, here at IIT Madras, and former postdoc who's now a faculty at IIT Tirupati, Aravinda. And these results partially appear in these papers. So I'm going to first motivate the problem and give some basic definitions, and move on to discussing how to construct so-called dual unitary operators and their properties, and finally talk about channels, quantum channels, which have relevance to many-body problems constructed out of these. So first of all, well known that it's a difficult problem to consider general interacting quantum many-body systems. Difficult in general for many reasons. Basically, also the fact that the dimensionality of the spaces is exponentially increasing with the number of particles, as well as the fact that non-integrability is a generic feature of many-body systems. And so the study of minimal models of many-body quantum dynamics, which exhibit some of this complexity, is of interest, contemporary interest. I would say that a model which is of relevance is this kind of a quantum computing model, where we are putting together gates and interaction between gates of many gates, like what is there in a quantum processor. For instance, this Google Sycamore experiment with some 50-odd qubits. And you can see these gates here, which are 2-qubit gates, which are connecting the single qubit gates. And my talk is going to be about these 2-qubit gates and special classes of 2-qubit gates, which will lead to complex evolution of this many-body circuit. It's quite natural to anticipate that the entangling properties of these 2-qubit gates, and these are all unitary gates here, will play a role, because that's sort of a proxy for the interaction strength in these kind of cases. But we want to analyze how far actually entangling properties of just these fundamental entangling gates play in this rather complex time evolution. These models have been studied for very long now, where you have random quantum circuits where you randomly choose pairs of qubits, and then you have 2-qubit interaction between them. For instance, it's some kind of averages can be calculated, especially in the large local dimension limit. So there are analytical derivations for quantities like entanglement growth, information scrambling, and so on. So I put some literature here. The kind of models which I have in mind are very simple models in which you can have the so-called brick wall models, where you have many particles. Here, for example, each of these small circles is a particle. Actually, it's a gate, but you can also think of it as a particle. And then you have these unitary operators, which is entangling these particles. So 2-qubit or 2-qubit in general, it can be any local dimension, entangles nearest neighbor pairs of particles. And then you have single qubit gates which are acting. And then every other neighboring gate interacts, so that by this time you have every pair of, there are no particles left alone. And it can produce rather complex states, and then you iterate this in time. So this is the iteration of time. So what happens in these models can be studied in many ways. One of the ways that we are interested in is correlation function. So you take some observable which is localized at one particle, and you evolve it in time, and you ask, how is this operator spread out? And typically it's spread out within the so-called light cone, which is a constraint which comes from the unitarity of these operators. So it can spread anywhere in this LO region. However, there are some special classes of these 2-qubit operators, which are called the dual operators, wherein all of these correlations in the interior of the light cone strictly vanishes. So they are having some solvable properties of that kind, and we need to only look at what's happening to the correlations on the light cone itself. And therefore, these are special many-body systems in which these 2-qubit operators are unitary. I mean, are so-called dual unitary. So these 2-particle dual unitary operators are, in some sense, unitary both in temporal as well as spatial direction, as I will motivate in the next slide. So this is what we will be calculating. Essentially, we'll be looking at, rather. It's already been calculated. 1-particle correlation functions of many-body circuits such as these are completely governed by completely positive trace-preserving maps, which are specified. These maps are specified by this 2-particle unitary operator U. So we'll be interested especially in properties of these CPTP maps, and we'll see why that is a central quantity. In some sense, these models are solvable. There are some exact results, for example, for correlation functions, even for finite local Hilbert space dimensions. People have studied various quantities, entanglement growth, spectral form factors, OTOCs, and so on. I've again put down some part of the literature. You can see the previous speaker, Thomas Guhr, was involved in, and collaborators were involved in some of the early work in this field. So to define a dual unitary operator, we first concentrate just on unitary operators, in fact, throughout the talk, which is bipartite. So it's local. You can think about it as two particles in which the local Hilbert space dimension is Q. So this unitary operator is just a matrix, unitary matrix of dimension Q squared. And that's the building block of this entire circuit. And here there is a representation, it's bipartite, so there are two indices. I and alpha are the input indices in some sense, so this is the space indices, I alpha, and that output indices J beta. It's kind of a tensor network notation of this unitary operator. So we may think of this as a time evolution, the vertical direction, and this as space. And then you can do time evolution. For example, you squared off this many body circuit, just putting together many of these unitary operators and contracting them in various directions. So that's space and time. Now, a dual unitary, first of all, a dual of an operator U is the special construction UR, which you're getting out of this unitary operator by just interchanging these indices I and beta. In this case, J and alpha. Okay, so this J and alpha here, so it's in a way, if we think of this vertical as time, the input now becomes time, I and J, and the output is this alpha and beta. So we have changed our perspective from an input being time to space. So it's in some sense, exchange between space and time, and therefore it's called a dual. But this operation is a well-known operation in quantum information. Much before this, it's been called realignment, and it's especially applied to density matrices. So in general, if you take a unitary operator and you do a realignment of it and calculate UR, it's just a permutation of these matrix elements, and it has no reason to remain unitary. Dual unitary operators are those special classes for which the realignment is also unitary. Recall that there is also another famous operation on bipartite systems called the partial transpose, where you interchange a particular subspace. Let's say this, in this case, the second subspace is interchanged, alpha and beta indices alone are interchanged. So there's a partial transpose of this, U gamma, which I represent as U gamma. So I just want to say that if U gamma was also a unitary operator, then this unitary operator U that you began with times the swap operator is a dual unitary operator. So you can construct dual unitary operators out of operators whose partial transpose remains unitary. So let's look at some basic examples of dual unitary operators. For example, the identity gate is not a dual unitary operator. It happens to be such that its partial transpose is unitary. And therefore, the swap gate itself is an example of a dual unitary gate. In fact, the realignment of it is itself, it's the so-called self-dual. Another example, which has been known for some time in a different way, is a Fourier transform just a discrete Fourier transform, considered as a 2-qubit operation. So it's a q-square dimensional Fourier transform. And this is also known to be a dual operator, but its realignment is not itself. If we consider 2-qubit cases where q is just 2, there is a general parameterization of dual operators, which is just given by this. It's looking like an XXZ model in which you have sigma x, sigma y, with specific phases pi/4. And sigma z, there is a j which can go from 0 to pi/4. So especially at pi/4, it becomes essentially the swap gate, and at 0, it becomes a different gate which is called a DC0. So in this case, also these are examples of self-dual gates. Now, an important property of these dual operators are such that if you take local unitary operators on these, then they still remain dual operators. So there is this freedom of choosing this. In the context of circuits, what it means is that you can have any single qubit operations, gates in between. The fact that this 2-qubit gate is a dual unitary does not change. So that's a nice property. So what is the connection between dual unitary operators and these circuits comes out from this connection between, as I said, the correlations are non-vanishing only on the light cone. And on the light cone, these correlations are given exactly like this, where this lambda j are eigenvalues of this CPTP map, which depends only on this unitary two-qubit unitary operator, and is defined in such a manner. So this is a single qubit operator, sigma. So you consider a sigma tensor identity, and you evolve this. So now this is an entangling operation on this, and you trace out the first system, and that gives you another qubit operator, a single qubit operator, and so that defines a map from single qubit operators to single qubit operators as written as M+. So we can think about this map. It's actually a CPTP map that becomes clear because we can write this in a vectorized form, so that the initial state is a vector which is of dimension q squared, and this M+ is now a matrix which is q squared dimensional, and explicitly it's given by this thing. So you see that this M+ depends on this unitary U in the following way. It's just the product of its partial transpose with its adjoint, and the whole thing you realign, and so that's what you get out of this map. So it's a known fact from the theory of quantum channels that every CPTP map can be written as a realignment of a positive operator, and in fact that positive operator is precisely this. So what we want to do is study these channels, especially for the case when this U is a dual unitary operator. But first, for that, we need to construct dual unitary operators in general. And I want to emphasize that this is itself not so obvious. If we take a unitary operator U and do a Schmidt decomposition of this in terms of product operators on subspaces, these are operator bases in subsystem A and subsystem B. They are orthonormal bases, and these are positive numbers. This is exactly just the Schmidt decomposition of this operator. Then these Schmidt numbers, because of the unitarity of U, are constrained to satisfy this relation. Q is the local dimension. Then these numbers can be found from a realignment of this U. So the realignment of this operator U is just given by vectorization of these matrices, MIA and MIB. And therefore, the combination of UR adjoint is a spectral decomposition where the singular values of this, or the Schmidt numbers are actually the eigenvalues of this matrix, or they are the single values of UR. So the realignment of the unitary operator singular values have this meaning of being the Schmidt numbers of the operator U. And importantly, they are local unitary invariants. And therefore, we can now define the operator entanglement in terms of entropies based on this SI. For example, the linear entropy, which is used heavily, is just given by this, the sum of SI squared. And in terms of this operator, it's given just by the moment of the second moment, UR adjoint. Now, if we have dual unitary operators, we just discussed that the realignment itself is unitary. And therefore, this is identity. And we get that the operator entanglement is as large as it can be, because this SI are all equal to 1. So it's a uniform Schmidt decomposition. So indeed, dual unitary operators maximize operator entanglement. So to summarize, this operator entanglement lies between 0 for product operators to maximum when they are dual unitary operators, including swap, which I already said was a dual unitary operator, and that's equal, this maximum is given in terms of this local dimension by 1 minus 1 over q squared. Now, I have to define two other quantities which are closely related to this operator entanglement. One is called entangling power, another gate typicality. The entangling power was defined by Zanardi early on. It's simply you take a unitary operator bipartite, act on it on product states, find out the entanglement of this, and then average over these product states. Turns out that if these product states are hard distributed, and if this unitary U, and if this measure of entanglement is this linear entropy of entanglement, then this is related to operator entanglement in this way, where this is the operator entanglement of U, this is operator entanglement of U times the swap. So, and this is the entanglement of swap itself. So this entangling power is related to operator entanglement. We defined another quantity called gate typicality, which has a very simple connection here. You just change the sign of this to minus and that to plus. And we'll come to a meaning of this shortly, but essentially it is this EUS quantity is related to the entropy of the partial transpose. Just as EU was related to the entropy associated with the realignment, this other one is related to the entropy of the partial transpose. So if the gate is a unitary gate, if this U is a dual unitary operator, then EU is a maximum that's equal to EUS, and therefore this entangling power is actually related to the gate typicality by this simple formula and is given by this. Okay, so if the operator U itself is partial transpose is unitary, then it's sometimes called a T-dual operator. And if U is a unitary such that is realignment and partial transpose are all unitary, the entangling power is 1. It's a maximum. It's called a 2-unitary, or it's also known as perfect tensor. So here are, if you take a unitary operators in, let's say, Q equals 2, these are all 4x4 unitary matrices. Here is a picture of what happens to entangling power versus gate typicality. They all lie in this shaded region. These are fractional powers of the swap gate. This is local gate 0. This is a swap gate. Maximum gate typicality, 0 entangling power. The C0 gate is here, DC0 gate is here, and it's in the interior of this curve. If we take Q dits for Q greater than 2, then EP can be equal to 1. There are perfect tensors. There are no perfect tensors for Q equals 2, so it does not reach there. But for 3 and above, there are perfect tensors and it reaches there. This is the line where you have dual unitary operators. This is the line where you have partial transpose to be unitary. Okay, so the construction of dual unitary operators are not obvious, because let's take a unitary operator Schmidt decomposition and replace all the Schmidt values by 1. You will get some U prime which is looking like this, and it has maximum entanglement. However, it's not guaranteed to be unitary. And this, therefore, is a constrained system. We had a simple algorithm, numerical algorithm, which will produce dual unitary operators, which just does the following. It's a map from the space of unitaries to unitaries. You take a unitary operator, realign it, and then find its nearest unitary, which is just given by the polar decomposition of this realignment. So the unitary part of the polar decomposition is the nearest unitary to that. And then you hope for the best and you iterate and you see whether this is going to converge to a dual unitary. So indeed, if we do this experiment, for example, we take random unitaries on of dimension 4. So they are 2 qubit gates, and they all lie on this part of the EPGT plane, entangling power gate typicality plane, as I just explained. They don't come till here. If you apply one iteration of this map, which I said, they all come up here. This is the dual unitary line of maximally entangled unitary operators. So you can see that they are pushed up there, and then they are further pushed up there till they actually lie on this dual line. So this is only after 5 iterations. You can see that it very quickly goes to dual unitary operators. If you do it for 3, this is the CUE, or the circular unitary ensemble gates. So they all lie here. They would all be pushed into dual unitary lines. Similarly, for 4, they would be pushed into that. And so here is a way of generating dual unitary operators. And here I'm showing some distribution of entangling powers, but maybe I will switch over from there and talk about other constructions. Here is a simple construction, because you can see that in these pictures, the entangling power of these are large. You have no small entanglement gates here, but indeed small entanglement gates can be constructed easily from these kind of block constructions of unitary operators here, and then you can just multiply it by swap to make it into dual unitary operators. Coming to these channels, which I talked about, which govern these many-body correlations, such as this, we are interested in the eigenvalues of this channel here for different classes of dual unitary operators U. And in particular, since this combination appears here, can the mixing properties be connected to quantities such as entangling power? But there is a caution here: the eigenvalues of these channels are not local unitary invariants. Indeed, single particle dynamics matters in the many-body case. So here, let me take a particular case of a dual unitary operator, which is given by diagonal operators multiplied by swap. And,
sorry to interrupt, but we have about 2 minutes left in the talk.
Yeah, thanks, Shashi. So we can find these eigenvalues here of this channel, and in fact, you can do that analytically and show that they are it's actually diagonal to begin with. However, if we have local unitary operators acting on this, it's no more diagonal, and the eigenvalues of this channel are all lying inside the unit circle, and except for the trivial eigenvalue, which is equal to 1. But there can exist eigenvalues which is equal to 1, which will indicate that the circuit is not mixing. Okay, so we look at these eigenvalues of this channel, and this is what we see for a particular entangling power of U, 0.09A. I'm showing the largest eigenvalue blue and the smallest eigenvalue in the red. And as we increase the entangling power, you can see that the smallest eigenvalue is shrinking, and so also is the largest eigenvalue. And you can see this more clearly as we are growing into this. And this black line here is this circle, which is having the square root of 1 minus entangling power. So this indicates that you can do a local unitary averaging and relate these mixing rates to the entangling power. So in order to do that, we have to control eigenvalues of these channels. And we use the Delphin theorem to control norms of these channels and do an average over local random unitary operators. And since there is no time, I'm not going to go into the details. But we argue that approximately this operator, this average of the largest eigenvalue, which governs the mixing properties of the circuit, is indeed related to the entangling power of this gate. And here I show this in QS 3, 4, 5, and 6. They all fall approximately, but to a good approximation within this curve. Here, the qubit case is very special and is very different. So to summarize, dual unitary operators are maximum operator entanglement, and they are useful as building blocks of many-body circuits. Our work has pointed to approaches of finding and characterizing such dual unitary operators, including numerical constructions of random maximally entangled unitaries. Channels that are mixing rates based on these dual operators are connected in a simple and universal manner to the entangling power of interactions in such circuits. Thank you very much for your attention.
Thanks, Professor Lakshminarayan, for an interesting talk. So we have time for like 1 or 2 quick questions. And I can see Arnab has raised the hand. So Arnab, please.
Hi, Arul, can you hear me?
Yeah.
So if I understood correctly, these dual unitary circuits had this property that these correlations were non-vanishing strictly on the light cone, right? So I was wondering if it's known that there are some, simple spin models with local Hamiltonians which actually have this special property.
Good question. So, as I said, in the general case, general meaning Q greater than 2, the exact form of these is not known, although we have all of these models of these. But for instance, the Cartan form, which I showed for the qubits, is an explicit form of that. So these are flow case systems in which you just have an XXZ kind of interaction here, this sort of thing. So, but these are all flow case systems.
So you mean to say that in these systems, the correlations would strictly vanish inside the light cone somehow?
Yeah. If you have 2 qubit gates of this kind and single qubit gates don't matter in the sense that the property still remains the same, you will be changing mixing rates and so on, but it would have precisely that. Yeah.
I see.
There are Ising models of that kind.
I see. Okay. Thanks.
Any other question? Okay, just maybe a quick clarification. So in terms of more traditional quantities like spacing distribution, etc., there is no difference between dual unitaries and unitaries, or there is?
Yeah, no, it's a good question. We tried to see if there was any, but I think even in low dimensions, we did not find any difference between dual unitaries or even maximally entangling ones where it's a two unitary operator. We did not find any difference in statistical measures because I think that the only properties that they seem to affect are really entanglement. So there is still fair amount of universality that way, that it shares these spacing distributions and so on look like CUE.
Okay. Thanks. So since there's no other question, let's thank Professor Lakshminarayan once again, please. And let me move on to our next speaker, Professor Samriddhi Shankar Ray.
Should I speak?
Yeah, please. So Professor Ray is in ICTS, International Center for Theoretical Sciences in Bangalore, and his main research interest is in fluid dynamics, magnetohydrodynamics, and deals with a lot of Berger's turbulence. And today he is going to talk about many body chaos in a thermalized fluid. Professor Ray, please.
Thank you very much, Professor Srivastava. My screen's visible, right? So let me begin by thanking the organizers very much for allowing me to give this talk. I'll present some sort of recent work from our group. Let me also apologize in advance, being somewhat of an outsider to the experts in the audience, because there will be large bits of this talk which are probably, quite trivial, but I hope it will be useful for the students and they will be forgiving of me. All right. So the first question that I would like to ask is, why are we studying this problem, and the problem as defined in the first slide? And the reason for this is twofold. So the first reason has to do with the many phases of many body chaos. So for example, if we think about the classical butterfly effect for Hamiltonian many body systems, these have been sort of in several recent works sort of used to understand the issue of loss of memory, ergodicity, thermalization, equilibration. Whereas we know, when one thinks of chaos, or at least the sort of background that I come from, is when thinking of driven dissipative systems where things are certainly out of equilibrium, and there are complex dynamical macroscopic structures associated with this. So the first reason why we were interested in this was essentially to find connections, especially in fluids, between dynamical structures and macroscopic thermodynamic quantities. So the question really is how to reconcile these two kind of apparently disparate roles of many body chaos. The second reason why we wanted to look at this problem was because of these sort of recent work over the last 6-7 years in quantum chaos, where the ideas of these out of time ordered correlators have been used as a diagnostic for quantum chaos. So you measure these chaps, and when the system is chaotic, f of t is necessarily large, and you associate a certain Lyapunov and a butterfly speed with these guys. And the consequence of this was this rather influential paper, which gave a certain bound on this chaos, which I've sort of highlighted. So the largest Lyapunov exponent is bounded by the temperature. So what we were after was, and that's the second reason for studying this problem, is for classical systems, what is this bound? So the next question actually is, how does one study this problem? In other words, what's the classical analog of these quantum TOCs, and what's the right model to study them? So again, I won't go through details at this stage, but the classical analog, but I'll use this as a crutch for the rest of my talk, was developed by Abhik Das, who was a student here, and several colleagues who sort of showed in this paper a few years ago that decorrelators, and I defined them right away, which were defined for the classical Heisenberg spin chain at infinite temperature, was a way to understand this phenomena. So what one does is essentially generate a random spin configuration. You make two copies of them, except that at one site, you rotate one of the spins just infinitesimally. So basically, the two systems A and B are identical at t equal to 0, except the spin at site x equal to 0. And now what you do is you evolve according to the Heisenberg model dynamics. And as you evolve, you measure this decorrelator, which is 1 minus the dot product of spins side by side, system A and B. And what one is able to see is that these decorrelators have a certain light cone. So this is a plot of the decorrelator in xt space. And what you have is that this is perfectly correlated inside the light cone, and outside the spins are completely dx2 is equal to 0. So essentially, there is a finite speed at which the information that there was a minor perturbation at t equal to 0 is spreading. So this brings us to the second step. So how do we find the right model where we can use these decorrelators to actually ask the questions we began with? So the temptation, especially for someone with my background, is to put these ideas to test in the most sort of natural and well-known example of chaotic systems, namely turbulence. The problem with turbulent flows is they're essentially driven dissipative systems, and everything that's sort of built up to the story, all of them had a certain Hamiltonian structure, which is clearly absent in a fully developed turbulent flow. So the redemption, if you like, is to kind of look for variations of the Navier-Stokes or the underlying equations of fluid mechanics, which are still nonlinear, are still chaotic, but retains a Hamiltonian structure, in this case energy conservation, and allows for statistical equilibria. So just to sort of emphasize in the first 6 minutes the story so far. So the goal, just to make, it's a short talk, so just so that we have the goal in mind, is A, to find the thermal bound on the Lyapunov exponent, and also to investigate this interplay. And the approach will be to use these decorrelators on a model system of thermalized fluids. So this begs the question, what are thermalized fluids, and what is the classical thermal bound on the Lyapunov exponents? So what are thermalized fluids? So let me give you a sort of a very brief tour of this. So we begin with the inviscid three-dimensional Euler or the 1D Burgers equation. I'll just comment on results from the Euler equation and not the Burgers because we don't have much time. Where you retain just a finite number of modes. So there's a compact support in Fourier space through what's known as Galerkin truncation. So essentially, these are your inviscid PDEs, which are sort of well-known and classic. And then you define this projector, which projects this into a subspace with a finite compact support of kg. So it just has finite degrees of freedom. And then you end up with what are known as the Galerkin truncated inviscid equations, same as this, except now you have finite degrees of freedom. So what's well known is that solutions of these truncated equations, unlike the parent PDEs, are chaotic and they thermalize within a finite time, and they exhibit statistical equilibria, namely energy equipartition, Gibbs distributions, and a strict notion of temperature. So for example, if you look at solutions of the Burger's equation truncated, which is in red, they show all these sort of noisy, white noise-like features. You can look at it in 3D Euler. And, if you have training in turbulence, etc., you realize that these solutions are nothing like the original PDE. In particular, which is important for us, is that if you look at the PDF of the velocity, you have Gibbsian distributions, which allows us to define temperature, and you can trivially change temperature in your experiments by just changing the amplitude of initial conditions. That's very useful for what we are going to do. And also you have energy equipartition, and they're sort of equally distributed across modes. All right. So with that sort of background in the remaining 4 minutes, let me sort of tell you how we use these thermalized fluids to sort of solve the problem at hand. By we, I of course mean these two fantastic students, Sugan and Dheeraj, and we were ably guided by Shubhro, from whom we learned everything that we know about these systems. And for a full reference, here is the sort of PRL where you can get all the details. So as I said, I'll just stick to the Euler equation. So what we do is we sort of solve the Galerkin truncated Euler equation on our computer. We wait for the solution to thermalize. So at finite time, you have statistical equilibria. So depending on the energy, which is conserved of the initial conditions, you get different PDFs of the velocity field, which allows you to define different temperatures. So that's the V thermalized, the velocity field of the thermalized fluid. And now what's the strategy? So we play the same game that was done for the Heisenberg model. We make a copy of the thermalized field, one system we call A, the other system B, where we include a minor little perturbation, which still ensures the incompressibility constraint, and at t equal to 0, around a small region at the origin, let's say, of the box. And then we evolve independently the solutions of this systems A and B, and we measure, again, point by point, the difference of the velocity fields between systems A and B. So here's a sort of cut of this of delta U. It's 3D, but we've taken a two-dimensional cut. So you see the perturbation or delta U starts to grow in this rather self-similar manner. With time, eventually systems A and B, of course, decorrelate completely. So delta U is basically order 1. All right. So now, having sort of computed delta U by measuring this difference in the velocity field, we are in a position to sort of define the decorrelator as a function of both space and time, so how far you are away, or we can sort of integrate over space because the evolution is self-similar and measure the capital phi as a function of time. Theoretically, what Sugan was able to do, and this was really a tour de force from Sugan, because we all know that the 3D Euler equation analytically is a nightmare, and it still remains one of the great unsolved challenges. But what Sugan was able to do was to write down a linearized equation for delta U, the same chap which goes into the definition of this decorrelator. So I won't go through the algebra, it's rather messy. It's a few pages in the supplementary material. But essentially, he was able to relate the evolution of the decorrelator phi in terms of the strain rate tensor of the velocity field. So del T, del phi is the two perturbations, del U I and del U J. These are Cartesian indices which sandwich Sij. So here was a way in which he was able to show how the dynamical structures in the flow control how the perturbation spread. And most importantly in my mind is that Sugan was able to diagonalize and solve it in the basis of the eigenvectors of the strain rate matrix, which is a very popular quantity amongst the dynamicists, and show that the perturbations align with the compressible direction. So he was actually able to show that when the dust settles, he gets this equation where lambda c is a negative number, the eigenvalue along the compressional direction. So with that, I'm running out of time. So eventually, when you solve it, you end up with very specific predictions of phi of t at short times growing as exponential lambda t, and at long times they saturate to a value which is constant, the energy per mode. The sort of remarkable thing is, theoretically, it was able to show that lambda is proportional to the number of degrees of freedom and square root temperature. So again, recall the quantum bound, which was linear in temperature, so then showed that it's square root in temperature, which kind of confirms conjectures by Kuchan or earlier numerical calculations on spin systems by Shubre and others. So are these theoretical results right? And I'm nearly done. So here are sort of measurements from numerics of phi versus t on a semi-log plot, and you see this beautiful prediction of Sugan being validated. So there's an exponential growth at short times followed by a saturation. I don't have time to go through every detail of this curve. Same if you integrate over R, the phi t, the global decorrelator. And finally, if you actually then go ahead and plot the Lyapunov exponents from about 50 different sorts of simulations with changing degrees of freedom, perturbation strength, perturbation scale, all of that, the beautiful result is that the Lyapunov exponents for all these systems fall on this square root t, ng square root t scaling. So this was wonderful, and it sort of underlines the classical bound on these Lyapunov exponents. And eventually one is able to relate this, since I spoke about memory, to the time scale associated with the autocorrelation function in the 3D Euler. The autocorrelation falls down, falls to 0, but when you actually fish out the time scales, you see up to a numerical constant, the inverse decorrelation time and the Lyapunov exponents are basically the same. So with that, I will end, I'm not on time, thankfully, and say that what we have been able to do in this work is to have a microscopic model, a classical microscopic model, which connects measures of chaos, Lyapunov exponents, with thermodynamic variables, at the same time incorporating the dynamical structures in the flow. And there are several sort of ongoing work in these directions. So hopefully in the next StatPhys, I'll get a chance again to speak about it. Thank you very much. And yeah, thank you.
Thanks, Professor Rick.
So my apologies. Yeah.
No, it's fine. So we have already 2 questions. I see Arnab has raised hand, and there's a question in the meet, which is, why are we talking about quantum limits when it's a Burger's equation or Euler equation?
Well, we aren't talking about quantum limits at all. The question that we are asking is for classical chaotic systems, which are completely classical. Can one find the bound of the Lyapunov on the temperature? It so happened that there were quantum results, and chronologically, at least I became familiar with those results through lunch table discussion. So the natural question was, can we find the corresponding law in classical systems? PK, I can't hear you.
But is it not proportional to t instead of square root of t? I mean,
where? In classical?
Yes.
No, so that's what we find, that it's proportional to square root t.
Okay.
It's not proportional to t. Of course, dimensionally, you could argue that it must be some inverse of a velocity scale, which will be sort of square root of energy, which should be square root t, but that's really stretching dimensional analysis a little too far. But that's one way you can argue.
Okay, maybe Arnab?
Yeah, hi, Samriddhi. So I had a very naive question. So you're looking at this complicated fluid, right? And then you're calculating various Lyapunov exponents from here. Why is it obvious that this bound only involves the temperature or some power of it in such a complicated system?
It's not obvious. So one question is, as we discussed, I mean, what can it depend on, if you want to argue in that sense? So it really could depend only probably on the energy and the degrees of freedom, right? So now once the fluid thermalizes, a lot of the complications that one associates with a driven dissipative system goes out of the window, right? Because at the end of the day, you're just dealing with Gibbsian distributions of velocity fields, which is why the analytical results were also somewhat doable. But the greater surprise is that why do perturbations align with the compressional directions of these of the strain matrix? So this was a surprise to me when Sugan came up with this answer. But if you think naively, what else could it depend on, right? Arnab? I mean, because I've thrown away the the only other thing it will depend on is the dynamical structures, which is captured by the strain rate matrix, right? Because it deals with all the gradients in the flow. So if you looked at the closed form equation, which of course within some approximations for the decorrelator, it has all these three components built in there. But, but there's not an easy sort of phenomenological way to sort of argue this.
Right, because at least for the quantum case, I know that this thing only holds for some very special sort of systems, right? It doesn't hold for all systems. So,
so here again, I mean, for example, the Kuchan's results were for generic systems. But if you ask me, this model, for me, that's because this is the model that I'm sort of familiar and comfortable with. That's probably the goodness to truth answer to the question. But I think I can see why these are the only terms which might stay.
May I interrupt?
It's an alignment issue.
Yeah, so I guess that we are running out of time, and let me thank Professor Ray once again for a wonderful and enticing talk. And let us move now to the next speaker, Dr. Shabana Shabnam. She is from Lady Brabourne College, and her research interest is soft condensed matter and liquid crystals, and today she is going to talk about a molecular field approach to pressure-induced phase transitions in liquid crystal, smectic nematic transition. Dr. Shabnam, please.
Hello. Am I audible?
Yes.
Okay. So good afternoon, everyone. I'm Shabana Shabnam from Lady Brabourne College, Kolkata, and the title of my talk is A Molecular Field Approach to Pressure-Induced Phase Transitions in Liquid Crystals, Smectic Nematic Transition. Now, before going to the detail of my work, I will give a brief introduction of liquid crystal. As we all know, there are two well-known phases of matter, that is crystalline solid and isotropic liquid. In crystalline solid, we know that there is both the translational order as well as the orientational order. But in isotropic liquid, there is no order. Liquid crystals are an intermediate state in between these two, where only orientational order is present and almost zero positional order. There are also different types of liquid crystals, namely nematic, smectic A, smectic C, cholesteric. Depending on the molecular arrangement, these liquid crystal phases arise. And in my talk, I will mainly focus on nematic and smectic A phase. So in a nematic phase, the elongated molecules in the system always try to align at a certain direction known as the director. And depending on the angle between...
Dr. Shabnam, sorry to interrupt. Can you make it full screen, your slide?
Yeah, sure. Yeah.
Yes, thanks.
Is that okay? Okay.
Yeah, thanks.
Thank you. So in nematic phase, this elongated molecule always try to align along some certain direction known as director. And depending on this angle between the molecular long axis and the director, the order of the system depends. this order is measured by order parameter, which is given by this mathematical formula, statistical average of P2 cos theta, where P2 cos theta is the second order legendary polynomial. And as you can see from this formula, when theta is equal to 0, this eta, that is the order parameter, equals to 1, and that is the fully ordered phase or the nematic phase. But when these molecules are randomly distributed, this order parameter becomes 0, which is actually the isotropic liquid phase. While in smectic phase, the molecules has some translational order because they form a layer structure, and within each layer, molecules are trying to align along the director. So, in case of smectic phase, as we can see, apart from the orientational order, there is some translational order. And so to describe in a smectic phase, we will need orientational order and translational order and some mixed order parameter, which is given by the which arises because of the interaction between the orientation and positional order. Now, to describe such kind of liquid crystals, there are well-known mathematical models for nematic phase that is given by Meyer-Soppe mean field potential, which essentially describes that as temperature changes, there is a first order phase transition between the nematic phase and the isotropic phase. And in case of smectic liquid crystals, there is a well-known mathematical model given by Macmillan. And here, as we can see in the potential, apart from the orientational term eta P2 cos theta, there are the translational order parameter term and the mixed order parameter term. So, as we can see, both of these potentials are very much successful in describing the temperature dependence of the liquid crystalline systems. But when we go for the pressure dependence of the systems, we see that there is no significant molecular field study for the pressure dependence. So basically, in our work, we have presented a molecular field calculation which is based on a very simple model for an isothermal isobaric liquid crystalline system. So this is our model where we have used isotropic terms as well as anisotropic term. And here U2, U4 are and A are some constants, and V is the mean molecular volume, which is basically total volume of the fluid per molecule. And in the here you can see in the last term there is eta P2 cos theta plus alpha sigma P2 cos theta cos 2 pi z by d. Here alpha is an important control parameter for the system, and alpha can actually affect the system in such a way that here any nematic phase can arise depending on the value of alpha. So here we have, as we can see in the isotropic part, we have chose the Lennard-Jones, familiar Lennard-Jones potential, and there are attractive part so that the molecules do not move too far apart to form a liquid, as well as there is a repulsive term to ensure that molecules do not collapse to zero volume under the attraction. And using basic statistical mechanics formulas and mean field approximation, we have studied the thermotropic behavior of nematic and smectic liquid crystals. So first, let us discuss the effect of control parameter alpha on order parameter and entropy. And in the plots, in the top is the order parameter plot, and in the below is the entropy plot, and from left to right alpha value is increasing. So as we can see at the left plot, the nematic smectic transition is second order, But when alpha value is increasing, this symmetric nematic transition becomes first order because there is some discontinuity at the transition points, and at the very highest value used here, we can see there is no nematic phase, only symmetric and isotropic phase. When we plot alpha, that is the control parameter with temperature and pressure, we have this kind of plots where the left plot is actually, we have reproduces from Macmillan's paper, that is our potential, using our potential, we have reproduces the same result. But at the right side, this is a new phase diagram which we have we got from by using our potential. And in the phase diagram, as you can see, there are two significant points. One is TP, that is the triple point where three phases, namely isotropic, nematic and symmetric meet, and TCP, that is a tricritical point where nematic and symmetric phase boundary, the phase transition changes from second order to first order. Next is the alpha phase diagram. As we have seen also in the order parameter plots, as alpha value increases, we can see the changes in number of phases. So for lower alpha value, we can have two phase boundaries and three phases. Now at alpha is equal to 0.55, we can see that at the lower value of pressure, the two phase boundary meets and give us triple points. But when alpha value increases, nematic phase vanishes, and we have also symmetric A and isotropic phase transition. Next, if we see the effect of pressure on the order parameters, at lower value of pressure, we have only symmetric A and nematic phase, symmetric A and isotropic phase, and that is first order phase transition. But when pressure is increased, we can see there is a nematic phase, and this is known as pressure-induced nematic phase. So we can see by increasing pressure we can have nematic phase. So we can in the summary you can say that our model potential successfully reproduces the known behavior of symmetric A, nematic, isotropic phase transitions, and the thermotropic liquid crystalline systems, the properties of thermotropic liquid crystalline systems have been reproduced very well, and they matches with previous experimental works. And we have also shown that the application of pressure strongly affects the stability of the nematic phase, as a result of which the nematic phase can disappear and a direct transition from the symmetric to isotropic phase occurs. And in this work, we have two free parameters, capital A and alpha, and with the success of our work, we are quite confident that based on these findings, by using different large range of parameters A and alpha, we can study different equicrystalline materials. And our work has been is published on Physics of Fluids, and here are my co-authors: Sudeshna Dasgupta from Lady Brabourne College, Kolkata; Navobroto Ghoshal from Ramshodai College, Howrah; Anando Dasgupta from IISER, Kolkata; and Shomin Kumar Roy from Jadavpur University, Kolkata. Thank you all for your kind attention.
Thank you, Dr. Shabnam. We already have one question in link, which is, I think PK is asking whether cos Z over D will average out or not.
When?
In your potential, I think you have two terms. One was Legendre polynomial plus alpha times Legendre polynomial multiplied by cosine.
Yeah.
And the question is whether this term will have any thing because it may average out. PK, is that the question?
Sorry, I can't hear. I can't hear you.
PK, did you ask the question? I think. Okay, maybe there's another raised hand by Sumitabo Kundu. Maybe you can.
Yes. Am I audible?
Yeah.
Yeah.
Okay. And my question is, how do you prepare your system?
Prepare my system in what sense? Because we have actually
No,
here
actually,
used,
yes. Actually, my question is, you are considering the pure translational order parameter cos 2 pi z by d, right?
Yeah. Actually,
and
in my work, I have used only the orientational order parameter, pure orientational order parameter, and the mixed order parameter, where both orientational and translational contributions are present. And for simplicity reason, we haven't worked with the pure translational order parameter.
No, actually, my question was if the elongated axis is not the proper z axis, then if it is an arbitrary axis, then how do you counter this pure translational order parameter?
Okay. So in that case, actually, what I think that we are considering smectic A phase. In case of smectic A phase, this is in the z direction. But if we consider another phase which is known as smectic C phase, in that case, that what you are telling, that the inclined axis that can happen. But we are considering smectic A phase here.
No, actually, my question was if for the smectic C phase, the director is along the perpendicular of the plane, right?
Mm-hmm.
But
maybe you can do this in discussion session, like.
Okay.
Yeah. So, is there any other question? If not, then let's thank Dr. Shabnam for a nice talk, and let me thank all the speakers from this session for such a wonderful talks and also keeping in time. And thank you very much. And let me handle the baton to Professor Sakuntala Chatterjee. Chatterjee, please.
Thank you, Shashi, for chairing the session so efficiently. Also, I would like to thank all the speakers for today's session. Now, I have a couple of announcements. We have the first poster session today, which starts from 5:50. So, we are using Gather Town, and there is a large number of people who are waiting to present posters. So